Materials and Devices seminar. My name is Hetchen, and I'm subbing for Bob today. He's traveling. So it's my great pleasure to introduce today's speaker, Professor Amir Yacoby. He is one of the most awesome physicists alive. Okay. Again, he's one of the most awesome physicists alive, in my opinion, and he's also my PhD advisor. Amir joined the Harvard faculty in 2006 after spending almost a decade at Weizmann Institute of Science. Throughout his career, he has focused on an unusually broad range of subjects, and including, he's a pioneer in many fields, including spin qubits for quantum computing, quantum Hall physics in graphene, scanning nitrogen vacancy center magnetometry, and finally, topological superconductivity. Here in the Center for the Center for Integrated Quantum Materials, Amir is the coordinator for the research thrust Topologically protected qubits, which will be the topic of his talk today. Let's join me in welcoming Professor Amir Yacoby.
So thank you, Hetchen. It's very becoming because the topic that I'll be covering today is, in fact, mostly led by Hetchen. So in the Center for Integrated Quantum Materials, we are launching a new thrust to explore topologically protected qubits. And I have three goals in this talk. The first is to give you some background about what this thing means. What are topologically protected qubits? How do you control them? And how do you detect their state? The second goal will be to give you a sense of how the center is planning on exploring these type of phenomenon. And so I'll give you a little bit of sense of past activities and ongoing and planned activities in the context of topologically protected qubits. And in the last part of the talk, if there is some time, I'll talk a little bit about some of the work that we have been doing over the past year and a half to explore this area of research. Some of this talk, parts of the introduction and the last part, will follow what I've presented last year. So I apologize for those who have been here last year listening to my talk on a similar topic. So since we're going to be talking about qubits, I thought I'd start with conventional quantum computing. So already, as much as quantum computing is unconventional, there in fact is already conventional quantum computing, and the topological quantum bits are going to be the unconventional side of quantum computing. And we're familiar with quite a few implementations of quantum computing, ways of storing quantum information in various quantum degrees of freedom, and I've listed a few here. For example, from our own work encoding information in spins, in the electron spins, superconducting qubits, where one stores information, for example, in the direction of a supercurrent that's flowing in a circuit. One has many other implementations going, ranging from trapped ions, spins in diamond, nuclear spins. So there's a whole variety of implementations. And what's common for all of them is this continuous block sphere that basically represents the state in which one could prepare a single quantum bit, where on the North Pole we have some, an eigenstate 1 and a 0, and we can, by controlling this quantum bit, basically create any possible state that's represented by the sphere. Of course, controlling these qubits is done by some physical quantities, like a spin we can control with a magnetic field. And what's common to all these things is what controls their state are local physical quantities, like a magnetic field. So a spin, if it's sitting somewhere in space, if it's sensing a magnetic field, it will precess. The fact that these qubits are sensitive to local controls means that they're also decohering because of fluctuations in these control fields. And so this is the general dichotomy that exists in the field of quantum computing. On one hand, we'd like to be able to control things, and on the other hand, we'd like them not to be sensitive to the same variables that we might not be controlling very precisely. And so the real question that's, launched this field of topological quantum computing is, can one have more robust quantum entities, quantum states, that are not sensitive to local perturbations? So it turns out that, and all of you know this, that in nature we have two types of particles, fermions and bosons. And the reason we have only two types, and we're actually looking for other types now, if we want to create these kind of non-local creatures, the reason we only have two types, fermions and bosons, is because of the topology of space. So if we're in 3 dimensions, so first of all, to mention that we can explain nearly everything that we see around us using fermions and bosons. Fermions are responsible, for example, to the periodic table, magnetism, neutron stars. Bosons are responsible for superconductivity, properties of light, heat conduction. So we can really separate a lot of what we know about nature into these fermions and bosons. And the reason we only have two is because in 3 dimensions, there are two things that we need to require. One is that all our particles are identical. So if I consider, for example, an electron, I have 2 electrons. They are identical. There is no way of distinguishing them, assuming they have the same spin. And so if I want to switch the state, so I want to look at the quantum mechanical state psi of R1, R2, the probabilities, all observables, need to be the same if I permuted R1 and R2. So this is just a statement about identical particles. And from this, one can immediately derive the relation that the wave function of particles R and R2 are related up to a phase to the wave function of R2 and R1, where I've just swapped the two particles. But I can do this operation twice. So I can swap again, which will give me double the phase. And in 3 dimensions, because all these trajectories of exchanging the particles from point 1 to point 2 are deformable, one with respect to the other, even if I have some kind of local dislocation or defect, requires, therefore, that the states are single-valued. And therefore, there are only 2 solutions to this equation where this phase phi is either 0 or pi, corresponding to bosons and fermions. Now, once we go below 3 dimensions, it turns out that the world becomes richer. So to a certain extent, 2 dimensions are greater than 3. Because obviously in 2 dimensions we can have fermions and bosons, but as you'll see, we can have other things also in 2 dimensions. And the reason is that if we have some kind of defect in my 2-dimensional plane, now no longer all paths can be deformed onto one another. If I have a hole here, some singularity, I cannot deform this trajectory into the other one, as I could in 3 dimensions. So if I follow the same argument, where I require that this equation holds for identical particles, I need to stop at this point where I can have that the condition for swapping 2 particles has a phase in it, and which means that the wave function is not single-valued. And that is something that we can have in 2 dimensions, for example. An example of this situation is the fractional quantum Hall effect, where under certain conditions, where the filling fraction is 1/3, this phase could be 2 pi over 3, suggesting that there are 3 possible values for the wave function, in fact indicating that the ground state is degenerate. But its degeneracy is rather small. It only has 3 varieties to it, given by these 3 possible phases. So the topic of topological quantum computing has to do with yet another type of possible particles in which that can again only exist in reduced dimensions, and whereby there is even a generalization to this thing where the wave function is not just related to the permuted one with a phase, but in fact the wave functions are in fact entirely different. And I'm not going to derive this kind of condition. I'm just going to argue that that's what happens, and I'm going to give you a little bit of sense of how do we get these kind of creatures that satisfy this condition. And because we have a richer possibility of this kind of arrangements indicated here, it turns out that for these kind of creatures that I'll describe in a bit, the ground state can actually be macroscopically degenerate and not only threefold or fivefold degenerate, can really have large degeneracy, and that is the space in which we'd like to perform computation. Okay, so in order to get a sense of what are these things that have this kind of non-abelian, and the reason I call it non-abelian is because swapping R1 and R2, coordinates of particle 1 and particle 2, does not simply give us a phase factor, but gives us a new state. All right, so I'm going to try to give you a little bit of heuristic picture of what makes up these entities. So we're all familiar with electrons, and I'm going to treat the operators that create or annihilate an electron as complex operators. Let's just think of them as complex numbers for now. And we can write a complex number as a sum of a real and an imaginary component, gamma 1 and gamma 2. And so this would be the creation of an electron. This would be the removal of an electron. And so what I can do now is I can figure out what gamma 1 and gamma 2 are just by looking at superpositions of C and C dagger. And these, as you'll see in a minute, these gammas are these elementary excitations that have this non-abelian character to them. And you already see that these, what I call Majoranas here, these are operators. They are superpositions of electrons and holes. And it already gives us a hint that if we'd like to find these creatures, we should be looking at someplace, materials or systems that have electrons and holes residing in them, and that would be superconductors. Superconductors have electrons and holes living simultaneously. All excitations of superconductors are superpositions of electrons and holes, so this is very natural. But since every electron can be described as these two Majoranas, there is yet another condition that we'd like to impose, because this was just a mathematical game. The other condition that we'd like to impose is that we are looking for systems where physically one could separate these two constituents. If these two constituents are just physically sitting exactly in the same place in space, they form an electron. And that state then is either occupied or empty. That's not very interesting. It's just a complicated way of describing an electronic system. So the really other ingredient is that we'd like systems in which we can physically separate far apart these two constituents. And when we'd like to know what is the state represented by these two Majoranas, we'd need to bring them back together to ask, is this electronic state occupied or empty? All right, so in order to see the richness of this system, let's consider a situation where we have two electronic states available. And the reason I'm saying you have two electronic states, I have four Majoranas. So if I combine each two, they represent one electronic state, and each one of these states could be either filled or empty. So here's my Hilbert space. These are the possible states that my system can be in. Either I could occupy both states, they could both be empty, one occupied, the other empty, and vice versa. And the reason I've lumped them into these two sections here is because these have the same parity and these have the same parity. And as it turns out, the operations that one is able to do within the system preserves the parity. So in fact, for these number of Majoranas, or electronic states, my Hilbert space is only twofold. I have only two possible states, for example, 0, 0, and 1, 1. So let's imagine that we start out with these two Majoranas, two constituents, very close together, and we find that this state is empty, has no electron living there, and here this state is not, no electron living here. So our initial state is 0, 0. It turns out that if I rotate one constituent around the other, it transforms my state. So if I start out with a 0, 0 state, and I just swap, rotate one, I exchange 1 and 2. This just introduces a phase. But if I exchange one from one state and the other from the other state, 2 and 3, note that I've ended up with a quantum mechanical state that is now a superposition of my possible Hilbert space. So this is a quantum mechanical transformation where I've now did some kind of operation, a gate operation, if you like, within this space, going from a state 0, 0 to a state 0, 0 plus I 1, 1. So this is a quantum mechanical operation which will be one of my gate operations when eventually I'll be building a quantum computer. Okay, so how can we look at things a little bit more interesting? So imagine we start again with the 0, 0 state. And now I separate my Majoranas. So now they're not overlapping, and they're just encoding some state. And if I didn't braid any one around any other, then in fact the state encoded by this system is still 0, 0. But now if I follow some of these braiding rules that I described before, if I just take 2 and surround it around 3 and bring it back to its original state, and I ask, well, what is the occupation of my 2 electrons here? It turns out that I've transformed this state entirely from 0, 0 to 1, 1 deterministically. So these are the kind of manipulations that one can do. There are 2 things that are important. One is braiding. That is what governs the quantum mechanical operations, how we're changing the states in the system. And the other is what's called fusing. We're bringing pairs of Majoranas together to ask, is the state occupied or not? And the combination of these 2 things are very deterministic in the sense that we can predict deterministically what is the quantum mechanical state and what is the outcome of, or the probability of the outcome of each experiment that we will explore, just as we're used to in quantum mechanics. So taking this one step further, as I mentioned, if I now have many more electrons represented by Majoranas that could be separated in space, these number of Majoranas encode a Hilbert space that scales as 2 to the power n over 2. And I didn't mention before, but you see, all these states are in fact degenerate as long as these Majoranas are not overlapping. So as long as they're far away from one another, these 4 states are entirely degenerate. I can only move within the sub-Hilbert space that preserves parity, but the other parity state is also the same energy as this one, in fact. So the important thing here for the context of quantum computing is that the way we braid these states is completely unimportant, because if I take number 2 and do a trajectory that does not encircle particle 3, I will not change the state. So the quantum mechanical state of these systems is completely insensitive to local perturbations, what happens to each one of these, and really require non-local operations that will basically take one around the other. Only at that point did I do an operation on the system, and now when I ask what's the occupation, I will get a different result. So that's the interest. These type of quantum bits are protected against local perturbations, and so very different from the original quantum bits that I described in my first slide, where these are sensitive to local perturbations. You see that in this particular system, the operations and the measurements are very, very different from one another. And so fluctuations in the operations are not really going to introduce any errors in this system. So the goal of our thrust within CIQM is really to develop materials. I haven't told you how we're going to make these kind of things, but to develop materials that are needed in order to generate spatially separated Majoranas. We're interested in creating hybrid structures. You'll see that we can create hybrid structures out of conventional materials that will host these kind of excitations. We'd like to demonstrate their existence, of course, demonstrate braiding, and demonstrate detection of the underlying quantum mechanical state. So these are really ambitious goals, but that's where we're headed within the center. We'd really like to try and focus on these aspects. And as you'll see, there are actually quite a few different ways of trying to achieve this goal. All right, so what are the materials in which we are going to find these kind of peculiar excitations? So it turns out that insulators have 2 types. We are familiar with topological insulators and conventional insulators, and the difference between them is that topological insulators are ones that have, when the chemical potential is in the gap, has surface states. They have excitations, electronic states that reside on the boundaries of the system. Analogous to that, superconductors, which are the things that we'd like to develop that would have these separated Majoranas, are also gapped in the bulk and come in two flavors. One are those that have nothing on their boundaries, and one that have surface states. And in fact, these surface states, because in superconductors everything is a superposition of electrons and holes, in fact, these surface states host Majorana excitations, and they could be extended or local depending on how we engineer the system. So to give you an example of topological insulators, because this is the analogy that I'm using in order to introduce topological superconductors, we have quantum Hall effect, which is a topological insulator. It's gapped in the bulk and has chiral moving edge states, so it has excitations along the edge. Time reversal symmetry is broken, so we have only one chirality. We have quantum spin Hall insulators that we're familiar with since approximately 10 years now, where again the bulk is gapped and the edge has counterpropagating electronic states. And note, the surface states for topological insulators are electronic in nature. Analogous to that, we have topological superconductors, chiral and non-chiral. These host Majorana edge states. And the important thing is that each one of these Majorana edge states carries half the degree of freedom of an electron, just the way I've introduced Majoranas as composing two of them, composing one electron. These are the excitations that live on the edge, and here they're really extended. For the purpose of quantum computing, we'd like to localize them. We'd like them to be localized so that we can reduce their overlap one with the other and perform these braid operations. So where do these edge states appear? They appear every time the gap closes. So here's an example of a superconductor where, of course, at the boundary the gap closes, so we'll have these excitations. But also, if we thread one of these topological superconductors with a vortex, the gap will want to close there, and at that point we will have a Majorana excitation. Yeah.
In practice, it sounds pretty nice. Topologically protected state seems to be living very long. Coherence will be maintained and everything that you need for your computation. But experimentally now, what's the manifestation of that protection? Because I know that in real systems, in real topological insulators, when they look at the surface states like that, they only stay coherent within like tenths of angstroms or so. And they claim this is because you really don't have a perfect insulator, you have some dopants and stuff like that, and because it's only a surface to volume ratio, anything in the bulk can decohere those states and make them die. So is there a experimental true realization of the utility of those states?
So that's where we're working towards. Worldwide, there has not yet been demonstration of a topological quantum bit. There have been several groups that were able to demonstrate, I think, convincing evidence that you have separated Majorana excitations. And in terms of topological protection, I'd say there are several things that would limit the protection of these states. So first of all, as I mentioned, one wants to have these particles separated far enough so that they don't overlap. Because once they overlap, then these two states that they're encoding become distinguishable. And luckily, the wave function of these things decay exponentially. So you don't really need, in principle, to go too far in order to have their overlap be really, really small compared to the time scale in which you're doing some manipulation, because eventually they will interact. What determines that decay, this exponential decay, has to do with the superconducting gap that they live in. So what we'd really like to do is develop topological superconductors that have very large gaps, because that will produce Majoranas that spatially decay very fast in space and would not require us to really take them too far apart and facilitate operations. The other thing that I mentioned was that the parity in the system is something that in principle is preserved. But we know that superconductors have quasi-particles. And even if you're at a temperature that's far below the superconducting gap, we know that superconductors have quasi-particles, despite the fact that you'd say you expect the number of them to be exponentially small, we still find them. And it's not entirely clear where they're coming from. But another challenge in the field is to suppress the number of these kind of floating electrons or electronic-like states, because they will flip the parity and destroy your state. So there are a lot of, this is really a forward-looking field. So I think that your questions are really good in the sense that there are going to be things that are limiting coherence, etc., in these systems. They're just going to be very, very different from what we're familiar with for conventional quantum bits. And we'll have to address all of these as time goes by. Additional questions? Yeah?
Is it possible to create arbitrary superpositions of these qubits, or is it more like a digital kind of quantum computation?
So the way I've introduced things here, you cannot create all possible superpositions. And that is one restriction of this particular topological qubits. It turns out that you have other systems, I'll mention them briefly, that have even a richer underlying ground state degeneracy, and there braiding these elementary excitations does provide universal computing. So with these realizations, some of the gates you can do topologically, some you will have to do non-topologically, which will introduce other errors, just like you have in conventional quantum computing. Yeah. So the complexity of this system is not rich enough in its simplest form, and one needs to actually eventually go to something that would have more complex, called parafermions. Okay. So I was pointing out that in topological superconductors, that ones that have these kind of surface states, you will have places to where you can have extended Majorana excitations and localized ones. One-dimensional topological superconductors are another place where you would find these, and it's nice because if this is a long superconductor, these excitations live at the edge, and the edge of a one-dimensional superconductor are its tips, and so these could be fairly far separated apart. And as I mentioned, in these type of realizations, in these topological superconductors, that's where you can create Majorana excitations that are physically separated from one another, namely they're not simply encoding trivial electronic states. I mentioned also that the way one would create topological superconductors can be from conventional phases, and this is really, I think, one of the biggest accomplishments of the field in the past nearly decade, is that we're now understanding that we don't need to look for bulk materials that are topological superconductors and would have these properties. One could actually take conventional constituents or nearly conventional constituents, pack them together in a particular way, and they will then have the properties that are needed, namely will become topological superconductors. So here are some of the examples of these phases. We need to be able to take conventional superconductors, conventional magnetism, materials that have strong spin-orbit interaction. They could be either topological insulators or not. They don't have to be. And if one combines them, then one can create the variety of physics that we're really interested in. So for example, if one takes superconductivity and either a topological insulator or even just a material that has strong spin-orbit interaction, what we know today is that we can generate what's called triplet pairing. So these are superconductors where the pairs are made out of either equal spins or they're triplets rather than singlets. And this is important because you need this property in order to have a topological superconductor. And we know that these kind of conventional ingredients can lead to spatially separated Majoranas. If you combine superconductivity, magnetism, and topological insulators, you can create chiral Majorana modes. And here one has additional ideas of how to localize them and take advantage of them for computation. So to give a concrete example of how this works, Let's start with a topological insulator. This is a two-dimensional topological insulator. It's a quantum spin Hall insulator, namely the bulk is gapped, and on its surface it has counter-propagating edge states carrying opposite spins. This is a state that has been observed, for example, in mercury telluride. There are claims that it exists in another semiconducting system composed of indium arsenide and gallium antimonide, and also recently in layered materials, specifically tungsten telluride. And I think there are other candidates in which this quantum spin Hall effect is believed to exist. So it perhaps is not a very rare state. If one now coats this edge where there are electronic states with a superconductor, one creates a junction here between a conventional superconductor and this peculiar edge here, quantum spin Hall edge, and this superconductor that connects between one side to the other now becomes a topological superconductor. And one of its manifestations is the fact that the Josephson relation for this junction here is fractional compared to a conventional Josephson junction where the current phase relation is just I sine phi. And in fact, recently there have been two experiments done that have claimed to observe this fractional Josephson effect, indicating the existence of topological superconductivity in its extended form. I'm saying it's extended here because here you have effectively Majorana modes that are overlapping the two sides. If one wants to localize them, one needs to introduce another gap, and this could be achieved using a magnetic field that will force spin up to scatter to spin down and will reflect the channel, the up channel to the down channel. Once you do that, you have these localized Majoranas that live somehow confined between two types of gaps. One is a superconducting gap, the other one is this magnetic field Zeeman gap. And that's where they would live. Their scale is going to be dependent on how big the gaps are, and that's how they will exponentially extend into these gaps. That's why we want the gaps to be big, and thereby the overlap between these particles to be small. This particular realization has not been seen yet, although it was perhaps the first theoretical prediction of the existence of how to create these kind of Majorana, spatially separated Majoranas in a physical system. So here I'd like to say a little bit about the structure of our center that is looking to explore these phenomena. So as you've seen, the physics behind these systems is rather complex, and we need to both develop materials, we need to have theoretical insight, and we need to put everything together in order to probe, see that these exist, explore braiding, and detection of Majorana. So these are the three pillars of this thrust with the names of the people who are going to contribute to each one of these pillars. There are other thrusts within the center, CIQM, and there is a good overlap between what we're doing in this thrust and the other thrust, in particular in the type of materials that are being explored, like searching for topological insulators or layered materials, and you've heard talks by Joe and by Philip about these things. So they feed in very nicely into the ingredients, these kind of building blocks that we can use to create these topological superconductors. So to give you a few examples of what we might be interested in doing. So I already mentioned that a particular hybrid structure consisting of a topological insulator, a magnet, and a superconductor would lead to a chiral Majorana mode. So we'd like to construct this, and so of course we can construct this out of usual conventional building blocks, namely evaporate permalloy and aluminum as the superconductor to create these junctions, but one could also look at novel building blocks, one that are made of layered materials. So for example, one could use superconductor that is made of niobium diselenide. These are layered materials, these are van der Waals materials. You can cleave them and create stacks of interesting materials. One can use magnetic layered materials like chromium iodide and CGT here, where these are known to have interesting magnetic properties to replace conventional magnetism. The substrate here could be either a semiconducting topological insulator, but it could also be one of these newly explored topological insulators like bismuth antimony telluride, possibly with vanadium doping. These have been shown to have what's called a quantum anomalous Hall effect, so a very good starting point for exploring Majorana excitations. Finally, as I mentioned in response to the question, that we'd like the energy gaps in these systems to be as large as possible because that will determine the robustness of the various phases. So we're looking to try and create these topological superconductors with the largest possible gap, and that would mean basically that we'd like the constituents to have the largest possible gaps. So we're looking to see, can we enhance superconductivity in any of these systems? So an interesting exploration that has started in China, where one saw that one monolayer of an iron selenide film on top of strontium titanate enhances superconductivity considerably. So you have interface enhancement. At MIT in Mudera's group, one was able to show that if you put a topological insulator on top of a magnet, europium sulfide, again, magnetism is considerably enhanced. Yeah.
Yeah, I noticed that you have these transmetal dichalcogenides there, but for exploiting their superconducting phase. But they also have some of them vial quasiparticles, which are the kinds that you might want.
So we don't want vials. We want really, so vials appear in what's called semi-metals.
Yes, yes.
So the bulk of the system is actually conducting. So for the purpose of localizing Majoranas, you'd really want gaps and not things that have states in them. So vials will not be very good. But yeah, you can create also these kind of excitations using, and these are not just transition metal dichalcogenides, there are trichalcogenides and so on. So these are all, but what's common to them are just van der Waals interactions. So you can easily peel them off and create hybrids. Okay, so I'm going to skip this. I mentioned already that some of the quantum computing operations that we'd like to do cannot be done using this particular realization of topological qubits. It turns out that there are other ways to realize that, and that is using quantum Hall states. So quantum Hall, as I said, is a topological insulator. It turns out that if one couples a superconductor to a quantum Hall state, one can create localized Majoranas. You see, one can create an effective one-dimensional channel where you have electrons going right and left. And if you create a gap in between, it resembles very much this kind of quantum spin Hall realization that I mentioned before. And you were going to get localized Majoranas at the boundaries here, at the tips. But again, this is the same kind as I described before. If one wants richer ground state degeneracy, one can imagine having these edge states be fractional quantum Hall states. And then it turns out that the ground state degeneracy becomes larger, and that does allow for universal quantum computing. But this is extremely challenging. Already coupling superconductivity to integer quantum Hall edges is very, very challenging, but nonetheless a topic that is being pursued in the center. Lastly, one could also create, I mentioned, a conventional structure that consists of a semiconductor, let's say, with spin-orbit interaction and a superconductor, and what was very beautifully shown theoretically by Falco, a postdoc here, together with Bert and collaborators at Weizmann Institute, was that if you consider two control knobs for this, so you can think that this is a wire. So there is some semiconducting materials, electrons are sandwiched between two superconductors, and there are two variables that one could consider. One is an in-plane magnetic field along this x-axis here, and the other is the superconducting phase difference across the two superconducting electrodes on the y-axis here. What was shown very nicely is that this system has a topological phase diagram that's shown here. Once you turn on a magnetic field, there are these big green diamonds in which the superconductor that resides here in between becomes a topological superconductor, and at the boundaries you would expect to find localized, spatially separated Majoranas. So the interesting thing is that, for example, when the phase difference is pi, note for all magnetic fields, one finds that this is a topological superconductor. So this becomes a very, very useful topological switch. It's very easy, just by controlling the phase at any value of magnetic field, you can tune in and out of this topological superconductor, thereby basically separating or fusing your Majoranas. The other thing that's really important about this realization was that it is very insensitive to details. So note, I've not indicated here what a chemical potential is. I've even not really indicated so much disorder. We'd like disorder to be low, but this system can't survive some low levels of disorder, and yet most of this phase diagram would look like this. So this is a very powerful implementation that we'd like to explore to be able to observe these kind of localized Majorana excitations. Now, how to realize this thing, there are many, many different ways. One is using, for example, layered materials. So here is an example where one takes this topological insulator or a quantum spin Hall state made of tungsten telluride and puts layered materials, niobium diselenide. That, with controlling the density here in the middle, would basically be a proper realization of this geometry. One could also even try to use graphene. There's been some recent beautiful work showing that when you put graphene on a magnet, on YIG, it actually acquires spin-orbit interaction. And you already have the magnetic field inside the YIG, so time reversal symmetry is broken. So this system might also exhibit the required geometry to realize this particular implementation. So there are many, many different ways. And one that we've been exploring in the past year, and I'm not going to tell you about it, I'm just going to indicate that, was using semiconductors, using mercury cadmium telluride, and I'd like to highlight the contribution of Hetchen, who introduced me, Andrew Pierce, Michael Kosowski, who are here, and Sean Hart, who was a previous graduate student leading this kind of effort. And here we were actually able to realize these type of junctions and see transport signatures for a topological transition that occurs as one ramps the in-plane magnetic field. And with this, I'd like to basically stop and take questions. Thank you for your listening.
Any questions? Don't be shy. I have a question. So
You should know the answer, though.
This is for the benefit of the audience. What's the advantage of these 2D realizations of this Qubit space compared to the 1D one that people are pursuing?
Right. Okay. So the one-dimensional ones. So eventually we'd like to braid things. So if you have really a one-dimensional geometry, you would need to connect wires in some kind of a grid format so that you can manipulate it. And there are there is an effort both in Copenhagen, I believe, in Delft, to try and create these kind of wire junctions in which you can try to transport Majoranas and braid them. The nice thing about the two-dimensional geometry is that using electrostatics, in principle, you could just easily move things around. You start with a two-dimensional geometry, so it's much easier to create whatever network you'd like for braiding and detection. You could also bring in whatever mechanism you'd like to detect these things. So remember, when you fuse these things, you find either a particle is there or not, and so you might want to have a quantum dot nearby. So in the 2D world, it's very easy to basically create all these things from an underlying two-dimensional material. It's harder to do it in 1D. You can ask, what are the advantages of the layered material approach to the semiconducting one that, for example, we are exploring currently? And I don't really know the answer except to say that, and you should know this best, it's really hard. So it might be that these have something going for them and become easier. They might be harder. We just don't know, so we should try.
Yeah, I think part of the difficulty is associated with the 2D nature. There's more space. That might be common to both approaches here.
Possibly. Yeah.
I have a question, but it's more detailed. I should have asked this question when you were speaking. When you were discussing the degeneracy of various states of this separated Majorana, 0, 0, 0, 1, and 2, that they were degenerate. In principle, these are topological excitations. In other words, they are long-range, they correspond to some sort of long-range distortions of some field in some space. Like, for example, vortices are going all the way to infinity. And so they're not localized excitations, so it's difficult to say that they're not interacting and they're completely degenerate, whether you superimpose them or you put them far away.
So they're localized in the same sense that every particle in quantum mechanics is localized. You know, our quantum world is made, you know, things are made of waves, and there is a wavelength to everything, and here the relevant wavelength is the coherence length of the superconductor. So they're localized on some scale, and as long as the distance between them is larger than that scale, then they are going to be relatively well
But in the example,
protected.
you had them also superimposed, and you said that kind of is degenerate.
So you need to bring them together. If you want to know what state you're in, what is that state, you need the measurable, the observable is occupation. Eventually we have electrons in the system, or electronic states, and we want to know, are they occupied or not? For that, you need to overlap these two half creatures, these Majoranas. They will then transform into either an empty or occupied state, and by measuring that, you will determine what the underlying quantum mechanical state is.
So you want to have a qubit sensor, but maybe this basis is not a good one. The occupation number representation basis may not be a good one to define your qubit.
Yeah, Bert.
And I think you can use any basis you want. Any basis is a good basis, but the actual state is that you wind up with, it may not be pure in this basis, right? And in particular, if you have a Hamiltonian, you try to diagonalize the Hamiltonian is usually not going to be perfectly diagonal in the basis that you have. So if you start out with something where you have, say, the occupation of a given pair, a certain pair is 1, let's say, so that's an odd parity pair. If there are other, this is a perfectly good state, but it's not an eigenstate of the Hamiltonian, and so if there are other Majoranas that are nearby, the actual eigenstate is some kind of a mixture, or you could say that you have eigenstates which are not, if all the eigenstates were exactly degenerate, then they would live forever. What causes something to decohere is the fact that there's actually an energy splitting. And that's what kills you. And the point is that the energy splitting between these many states falls off exponentially in the distance between them. So that's what you're hoping to gain. If you can get them far enough, exponentials can be extremely small. If you have exponential of a distance over some coherence length, if that distance is 100 times the coherence length, then you really don't have to worry about it. Now, unfortunately, the coherence lengths that we deal with here are typically hundreds of nanometers or something like that. So even if you separate them by a micron, you're not gaining as much as you'd like to. And that's what one is fighting. One wants to, this mathematical topological protection is in an ideal world where exponentials can be treated as 0. Exponentials are much better than 1/r cubed or something like that. But still, one is fighting that. And now the whole idea is, say, well, the exponential is not really 0, but they've gotten it where the exponential is at least this 100th. Maybe we can get it to, experimentally, it seems like we can get it down to 100th. If you can get it down to 10 to the minus 4, maybe that's enough so that you can do a manipulation fast enough so that you don't worry about this decoherence. So that's the thing that one is fighting, and it's really tough. But the thing about it is that exponentials are really nice. So if once you get your first, if you get it to 100, then getting it to 1,000 or 10,000 isn't necessarily so hard to imagine. You only have to get it twice as far or something like that. And so that's.
Let me ask one question on this. So it's not also the measurement? When you're making the measurement, you don't have easily separable, I mean, some clean basis.
Yeah, so what you want to do to make a measurement is actually make the difference in energy between, say, even parity and odd parity be, instead of being 10 to the minus 4, you want to make it 1 in some units, so you can really measure it. And that you can do by bringing them close together. as long as this pair that you're trying to measure stays far away from all the others, the parity is preserved. So you bring them together, and then you can measure that parity, and it's the same parity as you had before, provided that all the other exponentials are small enough compared to the time so that's what you're fighting. So you're willing to, of course, once you've brought them together, you've destroyed the coherence. You now make a measurement, and you don't have coherence anymore between that pair, but it shouldn't affect the other pairs. And okay, that's what you try to do. You try to set things up in some way initially, then you do a bunch of manipulations. Then at the end, you bring them together and measure, and of course that destroys the coherence. But meanwhile, if you've done the manipulations, maybe you've been able to do some kind of computation, and the measurement tells you what the outcome of that computation is. That's the sort of idealized dream. Now, whether Amir is going to achieve this, we'll see.
I mean, there has been more and more theoretical proposal for experimental detecting these. Actually, Gilad was Steven, Amir, and Bert co-advised for a paper on detecting these exponential decays.
Yeah, I do have a question actually. So when I was going to many of these talks back in 2015, there was a question of whether there's a smoking gun experiment to determine whether these things for sure exist or not. Back then there was still a debate. I've kind of lost touch with the discussion. So since then, has someone come up with a smoking gun experiment to determine for sure that these Marianas exist? I guess the second question is, would that be ability to grade them or something else?
So I think, if I understand correctly, what you want to know is whether the experiments that have been done, have those been smoking gun experiments to indicate that Majoranas exist? I mean, in principle, there are theoretical proposals that are definitely smoking gun experiments that would indicate that this is the likely physics. Of course, in nature, in physics, we never prove that we're right. We can only disprove things. But we have, one can devise experimental configurations that if you see a certain signature, it would be very, very likely that the underlying physics is what you're thinking about. A separate question is whether the existing experiments that have been done are of that nature. And, if I take each one of them separately, I'd say maybe I'd be a little bit hesitant. But I'd say overall now there is a growing number of experiments that are basically all emerging to be consistent with this kind of picture. So I think right now we do have experimental evidence that our understanding of these spatially separate Majoranas, in particular in nanowires, is a good picture to describe the physics that goes on in these systems. There are theoretical predictions and proposals for what the outcome would be upon braiding, and they are, from the theoretical point of view, they're a smoking gun. Whether the experiments, how clean the experiments will be, etc., is unclear yet. But yeah, I think the field is really on very solid theoretical footing, and experiments are, slowly showing consistency.
Any other questions? Yes.
Can I ask a basic question? In the beginning of your talk, you talk about the braiding operation can change a 0, 0 state into a 1, 1 state. So what would be the basis for a qubit in this system? And you also mentioned it's not universal quantum computing with Majoranas. And what's the limitation on the operation you can do?
So, okay, to really map out what is the space that you can cover with these braiding operations for these simple Majoranas will take some time. But already from the braiding operations that you saw that I can go from a 0, 0 to a superposition of 0, 0 plus I, 1, 1. And I can also go from 0, 0 to 1, 1. So already you can see that if you think of a block sphere of 0, 0 on one side and 1, 1 on the other, I already have pi over 2 and pi rotations built in. This is not enough in order to map out to do full quantum computing operations. I need additional gates. These are called the Clifford set. So there are more gates that I need. And some of these gates I cannot obtain just by grading, topologically protected, with this particular implementation. That's where these parafermions will become very, very important.
You can think of it that you're getting just 90 degree rotate by 2 pi over 5 or something like that, then you can rotate about different axes, and you can get things that basically are dense on the sphere. But with only, if you can rotate only by
Pi over
pi,
2
there are
effectively.
only 6 points on the sphere that you can never get to.
Yep.
You can't get anything else.
And that bread is good enough for quantum memory? Is that true?
No, because in principle you'd like to be able to store any quantum state, and you can't reach all quantum states using just braiding operations.
But with the memory, you don't have to braid.
Right, you need to store, but in principle you want to be able to store any state. So if your Hilbert space cannot represent every state just by grading, you're going to be you're going to.
Well, you can represent any state, but you have to do it. But you prepare the state by doing some operations that are not legal in the sense that are not within this.
Topological
If
protection.
you bring 2 qubits close together, you can produce
can do
other
anything.
things, but then they're not topologically protected.
Right.
The topologically protected ones
Yeah.
are only these 90-degree ones. So you can prepare any, in principle, if you're willing to
Operate them as
to
regular
operate them
qubits.
by bringing 2 together, you can prepare the states in a way that's not topologically protected and therefore may have some errors. Then you put them in this topologically protected. Then you separate them, and in principle, if the exponential can be neglected, you can hold them for an arbitrarily long time. So in that sense, it's a memory, and you can hold in that memory states that are not. It could be you could hold in a memory a state that's say 1/3 1 1 and 2/3 0 0 or stuff like that. You can store all those things if you've prepared them, and they'll stay. So I think in that sense it's a good memory. But then if you want to really do a topological computation, you do need to be able to get to other states. So you have to invoke things beyond. But the hope is that maybe you can do 90% of your operations using just these braid operations, and then 10% using the non-protected ones, and you really work hard to get the non-protected ones accurate, and that may give you an improvement. That's the hope. Why it may be still useful to use this.
And it's a starting point. I mean, it might be that eventually one does need to move on to these parafermions, etc. But we need to take baby steps here.